So our talk for our third Scholars Talk is Julian Gough, and his title is Recent Breakthroughs in Cosmological Natural Selection. Julian, thank you so much for doing our EDI Scholars Talk and helping us understand new changes, improvements to the cosmological natural selection theory, which many in our community really find fascinating, and some of us find very compelling too. I should say a little bit about you. I know you're an award-winning writer, and I saw that you've written the ending to the most successful computer game of all time, Minecraft. That was a great feather to lead with in your cap. You won the BBC National Short Story Award. You've published books in 37 languages, and starting as a writer, fiction and children's writer, you've pivoted in the last 10 years to more and more research in the cosmological natural selection theory, and then doing now original work in the space. And now you've been recognized for that by some of the some individuals like Jim O'Shaughnessy and Tyler Cowan, giving you grants for doing some of that work. So we're very honored to have you on board, and the floor is yours, sir. Oh, you're muted right now. At the moment.
I am muted. Oh, that's better. I'm honored to be here. Some of you guys have been very influential on my work, so it's great to be with people who've actually helped develop cosmological natural selection. I see Clement's here, and John, you're here, and Georgie. So this is great. Okay, I guess some of you are already familiar with cosmological natural selection, but I actually do want to start right at the beginning and run through the development of it a little bit, and then show how it's developed further since you last maybe checked it out. Because I think the developmental process of cosmological natural selection explains some of the problems it's had in gaining traction, and also explains why it's suddenly, I think, poised for a breakthrough. So, I mean, I think the roots of this theory go back to David Hume. I think, David Hume in some of his writings talks about his intuition that there were failed worlds before ours, that there were other worlds made and lost before we got to this one. And I think the intuition that you can't just start with a hyper complex universe was always there philosophically. But you need someone like Darwin to come along to give you an evolutionary theory, to give you a mechanism that can lead you to a complex organism style universe. So then Darwin comes along, and then immediately people like Charles Peirce, the pragmatist philosopher, pick up on it, and Peirce says, this seems like the logical explanation for the natural laws, physical laws, where there are regularities that are non-random looking and non-arbitrary looking, that have like complex consequences. They're the things that need explaining more than anything else, and evolution looks like a mechanism that could explain them. But you're still inside an infinite and eternal universe. That's the model we had, infinite and eternal. So there was nowhere, it was hard to know where the evolution was happening. It had to be happening inside an eternal, infinite universe. Okay, so that's where we are until the 20th century. And then you get the Big Bang. You get more and more evidence that our universe started at a point and expanded and developed from that point relatively recently. Given the quintillions of years old that a universe could be, or the infinite age that they thought the universe had, 13.8 billion years is not very long. So that's suddenly, you've got a very rapid development into complexity from a starting point that we now know from the cosmic microwave background is incredibly smooth and featureless. And I think cosmology completely failed to come to terms with the amazing shock that puts into cosmology. I don't think they really dealt with it very well. And I think that John Wheeler his breakthrough in saying that black holes and big bangs that might be opposite sides of the same phenomenon, that black holes in parent universes might give birth to child universes, was a kind of a key conceptual breakthrough into how you might imagine the reproduction of universes and maybe an evolutionary history of universes. And then Smollen's realization that if there's slight variation in the child universe, you're going to get Darwinian evolution of universes, I think was the great conceptual breakthrough in cosmology. And I think that the reasons behind it not gaining traction are partly because it came a little bit too far ahead of the observational evidence that would have helped support it, and partly they're sociological. Partly I think it was just it arrived at in the wrong place at the wrong time to gain traction. I don't think the reasons that cosmological natural selection isn't a big part of the mainstream cosmological conversation, I don't think they're scientific. I think they're mostly sociological. I think it's because he published his first paper in the Journal of Classical and Quantum Gravity, which it's a small, very specific readership that are not interested in evolutionary theories of the universe. And it just never crossed over to the people that could have developed it. And I think the fact that string theory dominated physics was bad for it, because you had this argument about the anthropic principle, and people like Leonard Susskind kind of squelched Smollen because it was really a rival theory to explain complexity. So, okay, that's where we are. People like John Clement, Louis Kane, Michael Price, I think really developed the theory in a really useful and interesting way by incorporating life into it. Why life? What's the, if there's an evolutionary universe and it evolves, there has to be some reason why life is being selected for, given how much energy and specificity to the basic parameters of matter are required to generate life. And the idea that life forms, once they get intelligent enough, manipulate matter to maybe generate artificial small black holes, that gives you a reason why life would be conserved in an evolutionary context of universes. So I thought that was a terrific breakthrough that wasn't given enough respect or attention. And again, for sociological reasons, I think. So when I got involved in this, it was because I had been thinking on my own about all of these things, and I came to the conclusion that an evolutionary explanation seemed like the most likely mechanism to explain why we had a self-complexifying universe that had a starting point of extreme simplicity and a rapid developmental progress to complexity, to hypercomplexity. An evolutionary mechanism seemed like the only sensible mechanism. So I look around and I discover there's already a theory about this, and that Lee Smollen has written very well on it, and that people like Clement and John have developed the theory further. And I grew fascinated by the lack of its presence in the conversation. So I over the last decade, I've got more and more interested in it, dug into it deeper and deeper. A couple of years ago, I realized that the James Webb Space Telescope was coming online. It was going to give us pictures of the first billion years of our universe, which we had never had before, and that this had to be a great potential experiment whereby you could actually test the theory. So I basically sat down and did a sort of first principles think through of the implications for the first billion years of our universe if cosmological natural selection was true and universes reproduced through black holes and big bangs. And the conceptual breakthrough I think I had, which has led to me making successful predictions and which has led to me getting funding to pursue this and so on, was that if you have universes reproducing through black holes, and presumably we're going to start at a place of supreme simplicity. Let's imagine the earliest proto-universes, they're not going to have a 90-something element periodic table. They're not going to have very complex structures like galaxies, and they're certainly not going to have planets and life forms. you're going to have the simplest and most basic forms of matter, and that's it. And you're going to have reproduction, and that's it. Okay, so you're just going to get black holes. And how do you get black holes without stars? How do you get them without technological life forms? You're going to get them by direct collapse. You're going to just get a Big Bang black hole cycle with ultra primitive matter that just collapses directly to form the new black hole, right? That's the simplest possible model. Direct collapse, and you're going to get very large black holes because you're not at the start of an evolutionary process. You're not going to get super efficient reproduction. You're just going to get this nice, simple, the simplest forms of it, and you're going to get direct collapse supermassive black holes. And you look around our universe, and you see supermassive black holes. You see black holes that are millions or even billions of times larger than a stellar collapse black hole. And it seemed to me that the logic of evolution would be that if direct collapse black holes were the way that the earliest universes must have reproduced, in the same way that prokaryotic bacteria are going to reproduce the simplest possible way, and anything more complex is going to happen much later down the evolutionary line, it's going to be conserved. If you see supermassive black holes in our universe that are millions or billions of times bigger than a stellar collapse black hole, they have to have formed by direct collapse. It doesn't make any sense to assemble them by many rounds of mergers of stellar collapse black holes. That's a more complex mechanism. Why would it throw away the simple direct collapse model to fancy up something much more complicated to get the same result, which is some supermassive black holes? So I figured that the logic of an evolutionary theory meant that the supermassive black holes we see in our universe, and there's one at the center of every galaxy that we've been able to observe close enough, would form by direct collapse, and they would form first. They would have to form first. Now, there's a bunch of reasons for that. One is just that's how primitive universes would have done it. They would have just gone straight into reproduction. But the other is because you need incredibly smooth gas to get large-scale direct collapse supermassive black holes. Because if you've got turbulent gas, or if you've got high levels of density fluctuation, you can't collapse a large enough cloud of gas to make a supermassive black hole. It's going to nucleate out into stars on the way down, and those stars are going to fuse, and you're going to get lots of little stars, right? So it has to happen early. So the cosmic microwave background shows you how smooth it was early on, and it shows you that there are very, very minor density fluctuations, like 1 in 100,000 density fluctuations in that early gas. And the model I've ended up with, which is looking good at the moment, is that it's the supermassive black holes that we have in our universe are probably emerging in a phase change very early on, triggered probably by those very small density fluctuations. Those density fluctuations follow a power law. There's a very small number of very big ones and a very large number of very small ones, and they follow a power law. The supermassive black holes that in the center of our galaxies also follow pretty much the same power law. There's a very small number of extremely big ones and a much larger number of much smaller ones, right? So the numbers kind of add up. So what you should get is I predicted what you should see when the James Webb comes online is you should get a universe where there's a wave of supermassive black hole formation, and it's the supermassive black holes that then optimize conditions for star formation, because the cosmic microwave background shows a very smooth universe that is not optimized for star formation. It doesn't have the kind of scattered local intense density differences you need for stellar nucleation, for forming lots of stars. But it does have the large scale, small density differences that would be ideal for supermassive black hole formation. So once you get the supermassive black holes, you get matter falling into those supermassive black holes. You get accretion disks, you get jets, and you shock the surrounding gas, nucleating out star formation. So I predicted you should see very early, very rapid, very efficient, very compact galaxy formation around supermassive black holes with strong jets. And what the James Webb has seen since I made that prediction is very early, very rapid, very compact galaxy formation around startlingly large supermassive black holes. If you look at UHZ1, that's a galaxy where 50% of the mass of the galaxy is in the supermassive black hole. This just hasn't been, this is not what we're seeing is not a bottom-up structure formation of the kind that lambda cold dark matter predicted. That's not what we're seeing at all. We're seeing extremely early, extremely dynamic, extremely compact, extremely energetic galaxy formation of exactly the kind that you should get in an evolved universe that reproduces through black holes and that conserved direct collapse supermassive black hole formation from its earliest times. So the model that I've developed, which has the working title of three-stage cosmological natural selection, just to differentiate it so you can see what we're talking about, says that there's three stages of development of reproductive success in our universe. One is direct collapse supermassive black holes. That gives you pretty much all the supermassive black holes you're ever going to get. They build galaxies around themselves. They build stars and galaxies around themselves. Those stars generate a lot of stellar mass black holes and continue to do so. Those stars, though, as in an evolved, highly evolved universe like ours, the stars go through multiple rounds of star formation, enriching gas as they go, so that you end up building out the full periodic table, so that by third generation stars like our own, you can have planets. There's enough material, there's enough metals, there's enough of the periodic table to build out planets around those stars. You get life, and ultimately you get intelligent life, and ultimately you get technologically produced black holes. So you've got basically about 1 trillion supermassive black holes. Then you get quintillion, and they happen right at the start, and you don't get new ones after that. There's no mechanism to build them after the gas is no longer smooth. You then get stellar mass black holes. But as well as stellar mass black holes, you get a much more complex mechanism of star formation that is highly evolved, that maintains galaxies over very long periods of time, continuing to make stars, continuing to enrich the gases, making planets, and forming life forms that then generate small technological black holes. So you've got three stages of reproduction inside the specific universe. Each of them evolved at a different moment in the evolutionary history of universes. And each successive stage requires more complexity in order to happen. But it builds on the previous one, so they're all conserved. This has a lot of explanatory power. For instance, if you look at the supermassive direct collapse black hole era, all that needed was maybe protons and electrons. It didn't need anything more complicated than hydrogen, because it's just going to collapse. That's all it's going to do. But to have stars, you need a slightly more complex chemistry. You need slightly more complex elements. So elements have to have evolved to be more complex. And in stars, you end up with an increasingly efficient star formation process, where you end up with the CNO cycle, which is carbon, nitrogen, and oxygen. So carbon, nitrogen, and oxygen evolved in the evolutionary history of in the line that led up to our universe, would have evolved for optimizing fusion, for optimizing star formation, and thus stellar collapsed black hole formation. but it gets exapted. It gets adapted by evolution for biological life and the next breakthrough into reproductive success. So it makes a lot of sense that the CNO cycle at the heart of stellar fusion, is the carbon, the nitrogen, and the oxygen are at the heart of biology. They've been exapted. They've been adapted to this new purpose in the same way that swim bladders were adapted to lungs when life went onto land. You can't just reinvent all of these materials from scratch. You have to build on what's there before. There's a lot of interesting potential explanations for a lot of interesting phenomena that also come out of a three-stage evolutionary process. For instance, the three generations of charged leptons, or fundamental particles, which are very hard to explain inside a one-shot random arbitrary universe model. Why are there three generations of particles? Why are there three charged leptons? Why is there an ordinary electron, a really heavy electron, and a really, really, really heavy electron? You could argue that this is very speculative, but I like these speculations because I find these very interesting. In a direct collapse supermassive black hole dominated universe, all that matters is mass. The more mass you can cram into a space, the faster you can get the collapses, the quicker the reproductive cycle. So something like the tau electron, which is massively heavier than today's electron, makes a lot of sense in that environment. You can imagine that electrons used to be extremely heavy, but as you move to needing stellar collapse black holes as well as supermassive, you can imagine the muon, or a less heavy than the tau electron, making it easier to do that. But as you need complex matter for life, you can see that as matter explores the possibility space, if you get a really light electron, the kind that we have in everyday life now, that will allow you to explore a much more complex chemical possibility space, which can lead to life and which can lead ultimately to reproductive success for the universe. Because each of these steps, you're getting a lot more black holes per unit mass. You're getting a lot better at reproduction. So anyway, those are some of the possible consequences of a three-stage model. Does anyone want to throw in any questions? I don't want to keep going endlessly.
That's a great time. Thank you for giving us that wonderful overview and giving us the opportunity to jump into questions early. The first one that I had in mind was, if you don't mind me going first, was there seems to be a teleology here that's, I wonder if you would call it selection or not, but like the original teleology of the Darwin and Peirce, seeing this idea that there's a replicative cycle here that's being maintained. Yeah. Would you call that selection, or would you call that just some like a constraint of cyclic development being required? Where does selection for you come in? And would you call that replicative thing kind of like the basic telos, a stable replicative system being the primary purpose or constraint that is required?
It's just reproduction. It's the simplest possible form of Darwinian evolution. There's just reproduction. They're not in competition with each other for resources, because the universes generate their own resources. They are both the organism and the environment.
Yeah. So would you call that selection then, or would you say this is kind of like the prerequisite to selection is having that capacity? I'm wondering, where does Darwin fit for you in this idea at the early stages of the, let's say, the supermassive replicator?
Just things that reproduce, there are more of them. And things that reproduce more, there are even more of them. And what you're going to get, you're just going to get a runaway movement towards reproductive success through black holes. You're just going to get the kind of universe that produces 2 black holes will do better than the kind of universe that only produces 1 of itself.
No, I see your point. So if there's anything limited at all with respect to, let's say, multiversal physics or multiversal capacity, then this runaway is actually going to have a selective effect. It's going to crowd out other uses of whatever multiversal stuff, right? That's your basic idea, right?
It's not even going to crowd it out. It's just going to massively outnumber it.
Right. Statistically outnumber in any sample. That's what you're going to find. Is
in any sample, you're going to find wildly reproductively successful universes more than others because there's just a lot more of them.
Yeah.
Lines don't go extinct. They just chug away.
Yep. Thank you. Georgie had a question. Georgie.
Yeah. So thank you, Julian. So just to clarify for myself, because I don't know if you mentioned it, but so there has been for a while a theory of primordial black holes, right? That form, but they form. They don't need matter, right? They just form from the fluctuations of energy. Yeah. So for this, because these supermassive black holes still form very early in the universe, do you think they form like from energy or from matter? Like, is it similar to the primordial black holes, or?
I don't know. I think I know. All I know is they form really, really, really early. I don't know, and I don't know how early. And in a way, it doesn't matter as far as the theory is concerned. What the theory predicts, what the logic of an evolved universe predicts, is you will get supermassive black holes as early as makes sense, and they will precede star formation. They will precede galaxy formation.
So the reason.
I love this. I really want to explore this further, Georgie, because there's a potential. There is a potential, for instance, for the tau or the muon to still play a part in this, because in the very earliest moments after the Big Bang, you do have a lot of you've got tau all over the fucking place, and that gives you an energy density that's much, much, much higher than you're going to get later, and it might even be a natural place for supermassive black holes to form. That stage, but I don't know how that plays out with the.
So the reason that I'm asking this is I'm trying to imagine, let's say, if we say that the physics constants, right, the fine tuning, which is now unexplained, we say, all right, the universes that could make more black holes, they had those constants, so they are more likely to reproduce. But if those black holes formed before matter, those constants wouldn't matter, right? If they were formed out of energy. So in other words, they wouldn't select for those constants because they were not necessary for the black holes to form, right? So I'm trying to imagine how this kind of black holes will select for those, which could be possible. I'm just out of curiosity, I'm trying to understand.
If they formed that early, if they formed ultra early, really, if they form when you've still got a lot, when you still got tau electrons hanging around, because if they form that early, what the way you would still end up with a complex universe is that by not using up all the mass energy at that point and leaving lots of it over, you will get a much more reproductively successful universe over the full lifetime of the universe, right? You're right, because you could get the mass energy at just after the Big Bang. You could get a relatively small number of supermassive black holes using it all up, but that universe isn't as reproductively successful as one that only uses up a very small percentage of the mass energy in supermassive black holes and leaves most of it over to form ultimately stars, human beings, technological black holes, you're going to get far, far, far more reproductive success over the full lifespan of the universe if you don't use it all up in direct collapse supermassive black holes. Do you see what I mean?
Yeah. So if you leave, but something has to determine that ratio, how much of the energy of the universe went into black holes and how much was left.
This brings up, if I can jump in, this brings up a question. What's the telos? What's the benefit to the universe of being more efficient with the primary replication so that there's extra mass energy left over? I can understand Jim Gardner's idea of the benefit to the universe of having intelligence. This is actually Edward Harrison's idea from 1995 too. Right. The benefit to having intelligence is we can screw with the basic parameters and fine tune them even a little bit better. Because we, that model makes sense to me. What do you think the benefit is to an early universe to having that extra complexity left over? How is it somehow a better, more robust replicator, or somehow better competition amongst other replicators, or would you characterize it in a different way?
You don't need the breakthrough to happen. The breakthrough isn't going to happen in one go. So what you're going to have is what's happening here is your matter is exploring a possibility space.
Okay.
Right.
So what you're saying is an exaptation, basically. The extra matter that's left over is an exaptation that does not become useful until you get something that can actually mess with the parameters.
Yeah. So I would imagine, you probably let's do a thought experiment here. That we go infinitely far back and we start with the infinitely simplest universe, and it's just mass energy expands, collapses, expands, collapses, expands, collapses. And at some point, it's shuffled in such a way that it expands and collapses into two. So you just had a black hole Big Bang of everything, and then it collapses and there's two of it. Now those two are if they're slightly different from each other, one of them will collapse and bang. Maybe they're producing two universes each time because that's how the parameters played out. And off they go. Each child universe then goes off exploring the adjacent possibility space for that kind of matter, right? But it's blindly exploring the possibility space. It's a sort of random walk. It's a series of random walks through the adjacent possibility space. And some of them will head off way over there, and some will head off way over there, right? All of them will continue as long as they can reproduce, as long as they can produce a black hole, they will continue. Some of those offspring might be more successful. Okay, so you've got this branching. But eventually the whole possibility, a lot of the possibility space gets explored. But you can imagine now we've moved along a bit. There's a universe that produces lots of supermassive black holes and is therefore pretty reproductively successful. Lots of supermassive direct collapse black holes. But then some of its offspring are inefficient at producing their direct collapse supermassive black holes, and there's a lot of matter left over. Now there's matter left over, but that matter may have the potential to do stuff that some of these slightly less efficient universes with matter left over, that matter will have qualities that allow it to do something more interesting, and at some point you get a kind of matter that can instead of just doing direct collapse can fuse or can do a proto-star type thing, or can form a smaller kind of black hole through a slightly different mechanism. And it's producing more offspring because they're smaller black
holes. So it's an excitation until you get the first stellar black holes, and then suddenly it becomes this very powerful new tool. Yeah,
huge reproductive success. Anything that's descended from that line is going to be, there's going to just be far more of them. So they're just going to be much more reproductively successful. There's more of them. Now you're exploring that possibility space that matter has shuffled into blindly. You're exploring that possibility space far more intently because there's a lot more offspring to explore it. So do you see what I mean?
Yep.
And you'll end up with more and more efficient kinds of star just by exploring the possibility space for that kind of proton, that kind of electron. This is something I've talked to you about, John. One indication of the possibility that we're talking about an evolutionary mechanism here is the fact that there is a fundamental particle electron and a complex particle proton. because that is actually a very nice way to evolve matter, because if they were both highly complex and both able to change considerably in relation to each other, it's very hard to get a stable inheritance.
Mm-hmm.
But if you have an electron that's pretty fucking stable and a proton that's hyperdynamic and complex, which we do have, that's actually a better mechanism for evolution over time. It's got the stability and the exploration going on.
Interesting. Jim has a question.
Sure.
Yeah, this is fascinating. I enjoy listening to this, and it's overcome some of my skepticism. So I have kind of a couple questions.
Sure.
And partially just to make sure I'm understanding. So,
yeah.
So you're envisioning this universe that, you know, I can think of it in two ways. One is like evolution, where you have lineages of organisms, and then or in development, in ontogeny, you have cell lineages. So the basic process is reproduction in both of those cases. And, you know, and in biology, you got mitosis is the basic, or cell division is the basic thing. Yeah. So my first question is that in the universe, with going back to the very beginning, where you have one giving rise to two, and then maybe two into four, et cetera, is that just totally stochastic? I mean, is it just random? Is it, you know, what is, because as a biologist, I understand this very well about how cells reproduce. But, you know, is when it comes to a singularity expanding and then collapsing, and, you know, you know, is it just stochastic? And then the second question is related. Is that still going on amongst these supermassive black holes out there? Are we propagating universes within our universe?
So I think that the earliest, the further back you go, the more stochastic it kind of is. But once you get into something as complex as ours, it's no longer entirely stochastic, because it becomes very meta and reflexive. And we are an element of the development of the universe, and where it goes next kind of depends on what we want.
Right,
not just what the
developmentally constrained at this point. So that's a very developmental kind of perspective. So I understand that. But at the earliest stages is I'm getting, I guess that's where it's
much more, I think, it's much more random at the start. It's very random. But I think more so at the start.
That's kind of how that also fits a developmental perspective, because as in early development, things are a lot more chaotic.
Yeah, that feels right to me. But in our universe, like from our universe's point of view, a supermassive black hole, a direct collapse supermassive black hole, creates an offspring. A stellar collapse black hole creates an offspring. If humanity end up burning through the uranium and the star goes out, you know, the sun goes out, and we kind of need an energy source, and we manage to put a lot of resources into creating small black holes, and we throw mass into them and turn it into energy, that's reproductive success for our universe as well. So from our universe's point of view, these are all good. It's just that a direct collapse supermassive black hole uses up a huge amount of resources to generate just one offspring, whereas the same mass could generate millions of stars and millions of offspring. And the same mass that's in the millions of stars could produce trillions of small Mount Everest mass technological black holes. So do you see what I mean?
Right, but does that mean that our universe is basically propagating itself via these black holes out there? Is that
Each black hole creates an offspring universe outside of this space-time, outside of our universe.
Okay, that's what I was driving at. Yeah,
you basically bud off a whole new bubble of space-time outside of our space-time when you go through the black hole. When mass energy disappears from this universe, it really disappears from this universe. It's not coming back.
And the problem I have with that is, how do you test that?
Yeah, it's hard. It's hard. We've got an N of 1. It does make it difficult. What I think you do is you look for traces of evolutionary history in the N of 1 that you have. In the same way that if the only thing you had was a giraffe, one giraffe, and you could probably work out something about the evolutionary history of that giraffe from just studying that giraffe really intently. Why is there salty water in every cell of its body? It probably developed in the ocean, ultimately. You know, why does it reproduce by fertilizing an egg? That's probably a retained mechanism of reproduction from the ocean. And so on and so on. Do you know what I mean?
Yeah, thank you. That's great food for thought.
And I think we can do that with this universe. Here's something interesting. Oh, sorry, Georgie. Oh, let me just finish this one and then I'll get to you. There are a bunch of really odd phenomena, quirks of physics in our universe, right? Something very interesting happens if you, instead of trying to solve those quirks or just throwing up your hands and going, well, that's a funny quirk. If you look for the downstream effects of those quirks on the reproductive success of the universe, if it reproduces through black holes, you will often find a reason for that quirk. It's a conserved mutation, right? Here's a great one. There aren't any stable nuclei with 5 or 8 nucleons. Why? There's no answer to that inside a mainstream random universe arbitrary properties. There's no stable nuclei with 5 or 8 nucleons. But if you think, what are the downstream consequences of that? You realize that if there were, pretty much all the matter in the universe would fuse chaotically into all kinds of elements during the first 20 minutes, the first, you know, of the after the Big Bang, because the temperature and the pressure in that first 20 minutes is enough to fuse the shit out of everything. It's higher than you get in the core of a star, but you don't get that because you can't, because hydrogen can fuse to helium, but helium, you can't, helium and a hydrogen won't fuse because there's no stable nuclei with 5 nucleons. And two heliums can't fuse because there's no stable nuclei with 8 nucleons. So fusion stops dead, right? And lets all that hydrogen get through that bottleneck, through the deuterium bottleneck, till it's past that point of danger. And then you're able to play out maybe direct collapse, supermassive black holes, stars, planets, the buildup of the periodic table, all the nice complicated stuff that happens in our universe. It couldn't happen if there was a stable nucleus with 5 nucleons or 8 nucleons. Isn't that very interesting? It's very like what you see in human beings, where the female hips are canted for childbirth, not for running, they're not canted for the benefit of the woman to make it her better at running or walking. They're there so that the child's head can get out through the pelvis, right?
Well, yeah, but I worry about just so stories. I mean, that's always the problem in evolutionary biology. You know, that the world is full of just so stories that explain things that you know. So I remain a little skeptical.
Sure, but the consequences of that. It's an extremely strange form of fine-tuning that you have stable nuclei with every number of nucleons up to they start getting unstable again around uranium or whatever, but a little earlier. But the two that are not stable are the two you need in order to allow for complexity. That's kind of interesting, right?
It is, for sure.
Yeah.
Thank you.
Georgie, did you have your hand up?
Yes, so thank you. So I was just trying to imagine, like, let's assume for the sake of argument that this is what happens, like you get the black holes and you give birth to other universes. So presumably all of the energy that goes into black holes has to form the new universe, so it has to move into the other universe.
Yeah.
But it's still here, right? So we kind of like for billions of years they exist and exert gravitational kind of attraction of the galaxies. So how can we get both? How can we get the other universe at the same time that we have the energy here? Like, where does it go?
Yeah. Well, I don't know, because
All right.
general relativity breaks down, quantum mechanics breaks down in a black hole. Nobody fucking knows. But what seems to be the case is you can generate a full-scale universe out of nothing. The mass energy in our universe and the gravitational energy in our universe net out to zero. So you can probably it looks like you can create child universes from scratch, from nothing. This is why it doesn't matter how big the black hole is, you can still create a full-size universe, even if it's quite a small black hole. This seems to be true. Like Stephen Hawking's written about this, Lawrence Krauss has written about this. He wrote a whole book, A Universe from Nothing, about this. The way you can generate, because also you can generate positive negative pairs and have them differentially annihilate. So the once you've gone through the singularity and bounced, it's perfectly possible to generate an entirely new space-time with an entirely new full-size universe of matter for free.
So if it's from nothing, then why do we need the black hole? We could just generate universes through some other mechanism. Yeah.
Well, why do human beings reproduce the way they reproduce? You're stuck with your evolutionary history. Material reality has a history, and you're kind of stuck with it.
Sure, I could jump in and speculate that you need the black hole because that's the inheritance parameters. A replicating system that conserves inheritance parameters rather than just randomly reproducing is going to outcompete the others because it has a developmental plan.
Yeah,
it's going to decide which pieces of that plan it wants to conserve and which ones it's going to allow to vary. So I can see that. Clement's jumping in.
Yes, so I think one way to answer Georgie's question is that actually, ultimately, what you're doing when a new universe pops up is that you are violating the first and second law of thermodynamics. So the first law, because you don't need new energy. Yeah, as you said, indeed, the balance between matter and energy in a universe is always equal to zero, and you bypass also the second law because you start anew, so you don't have the second law that applies to the new universe. Even though the parent universe will eventually die, the child universe could start from scratch, kind of.
Yeah, you sort of reboot. Yeah. There's some other seriously interesting.
Yeah, what you're basically saying is those laws are only applicable within any particular space-time.
Yes.
Yeah.
That's cool.
There are other implications of this that I posted yesterday, and I haven't talked about at all, and I'd love to talk about them because I think this is really important.
By the way, I just want to say we just lost Terry Bristol, who loves talking about entropy. You just scared him away when you said that, Clement. Exactly as you said it. Terry, I'm sorry. Come back.
Come back, Terry. We love you. I'm so sorry. Okay. I want to walk through the thing I posted yesterday because this is really interesting. And this only really occurred to me like 5 months ago, and I've spent the last 5 months writing this. So I want to test it out on you guys. I ended up calling it the blowtorch theory of structure formation to give it a snappy title. But listen to the implications of what I just said earlier. If the supermassive black holes form by direct collapse first, if they rapidly generate the galaxies around themselves, and if they're blasting jets from that early, because we're talking about this could be happening definitely inside the first 100 million years and possibly the first 50, which very possibly the first 50. We have jets firing from every supermassive black hole right at the start at redshifts that mean that the entire universe is 9, 10, 15,000 times denser than it is today, right? It's massively smaller and massively denser. So those jets are going to have structural effects on the universe. So the model I've laid out in the blowtorch theory is what you're going to get is the jets, as well as shocking the surrounding gas and nucleating out stars and forming galaxies, which is very clearly what's happening when we look through the James Webb. Those jets keep on going, and they are pushing. They're creating. We know the Fermi bubbles around our own Milky Way, which we saw in 2010. We're creating huge cavities in the gas, right? They're shocking out the gas north and south of the galaxies to tremendous distances. And those huge cavities will have electromagnetic fields laid into them because they're being pushed out by a massive electromagnetic jet. You'll get gigantic cavities, which will continue to expand as the universe expands, which will join, and probably like electromagnetic bubbles, they will join and merge into balloon animal shapes over time and keep expanding. And the path of the jet will leave a much stronger electromagnetic trail, that jet. And my argument is that is the actual explanation for the voids and filament structure. The voids are the cavities made by the jets, joined, merged, and expanded with the later expansion of the universe. The filaments are the paths of the jets, which maintain their electromagnetic structure over time and channel the gas. So what you're creating are reservoirs. You're pushing the gas out of 80% of the universe and it's channeling back over time. It's fed back over time through the filaments to the galaxies, because it came from the galaxies, so it goes back to the galaxies. That's where so the filaments feed the gas. They drip feed the gas back into the galaxies over the next multiple billion years, so you can have slow, steady star formation of the kind you need to generate life, because you need at least three rounds of star formation to get enough of the elements to produce complex, planets and moons and so forth, right? So you lay down the developmental, you lay down the structure of the universe right at the start, actively, not passively through bottom-up structure formation that very slowly makes things come together over time. You have a very active, early, dynamic era of structure formation that lays down the voids, the filaments, and the nodes that we see today. Okay.
So two questions. First, main question is that filament emerging because all those jets are doing their work inside of a boundary layer, because there's in other words, the Riemannian space-time, you go in any one place and you come to the same place from the other side, right? Because everything curves in 4D space. Uh-huh. Is that the assumption that the jets, there has to be a bounded space in which each of these supermassives are doing that, or is it something else?
You don't need a bounded space. Okay, you've just got an expanding ball of gas. Supermassive black holes form. They generate galaxies. They blast jets. This is just jets going through gas. They're just pushing the gas out of the way. It's not complicated. We know jets push gas out of the way, right? And we know they leave electromagnetic traces. I'm saying the voids are the cavities that were pushed out of the way, blown up massively by the subsequent expansion of the universe. And the filaments into which the remaining gas has been pushed and which then feed back into the galaxies are basically the tracks, the joined together electromagnetic tracks left by the jets.
You're arguing that electromagnetic effects are more important than gravitational effects for creating that filament?
Yeah. That's exactly what I'm saying. That's what I'm saying. The gravity does its thing, but all you need is baryonic gravity. You don't need dark matter. This means you don't fucking need dark matter for structure formation. the structure is formed dynamically by the jets in the extremely early universe. The universe lays down its own structure right at the start. And it lays down a structure that it needs in order to have long-term maintenance of star formation in galaxies, because they need to be drip-fed gas over very long periods of time to have ongoing star formation. Galaxies, we have some galaxies that don't do that. They're the ellipticals. The ellipticals make stars really, really fast and burn out. My argument is ellipticals are a kind of an evolutionary hangover from the earlier stage 2 universes that only did direct collapse supermassive black holes and stellar collapse black holes and didn't do life and didn't do technological black holes. So all they had to optimize for was star formation. And ellipticals are great at really rapid star formation, but they've got no long-term gas distribution system to allow for multiple rounds of star formation that allow for building out the periodic table, building out life.
Fascinating. I see.
Nice.
So that's another signature, if you will, of
Another
that,
signature of an evolutionary history.
of that hierarchy. Yeah,
Yeah.
fascinating.
Yeah. You've got traces. We have an appendix. The appendix is okay, but we've got a tailbone.
Is there evidence that ellipticals are kind of more primitive in structure then, like the way archaea are?
They're more primitive in structure. Yeah. They don't have that kind of. Spiral galaxies have a complex circulatory system. Gas gets delivered into the arms. It gets refrigerated because the carbon and the oxygen soak up the photons to let it cool, so it can condense and it forms stars in stellar nurseries. Right? There's a huge amount of very dynamic, active star formation going on in a spiral galaxy. Ellipticals don't do that. Ellipticals just make a shit ton of stars and burn out. They're red and dead. Mostly they're red and dead. When you say that to people, some will say, oh, but there's still some star formation in some ellipticals. Yeah, only when they crash into each other by mistake, and that brings in fresh gas. But basically, they're red and dead. So, and they're only maybe 15% of the galaxies. So they're, I think, a hangover. You can see the evolutionary history in our single example universe, because it can't just abandon the stuff that it built on. There's traces of it there. In the same way you can get the tau electron and the muon electron. They're ghosts inside the quantum electron field that, under extreme circumstances, you can bring back up. But the basic parameters of matter have evolved away from them over time, so that in everyday life in this particular specific universe, you're just going to get the ordinary electron. Do you see what I mean?
May I ask a question? Maybe Jim will jump in on this one. One of the things that's really interesting to us in our community is this idea of convergent evolution as a possible signature for what we might call universal development. Right. That on other Earth-likes, we're going to see these convergence. We have a few natural experiments with continents and placental and marsupial mammals, etc. Northern and southern polar fish.
Yeah.
Do you think you can see signatures of convergent evolution?
Yeah.
Where things start off differently in different locations in the universe, or different galaxies, and then isotropically they start kind of converging because they have to, basically.
I think there's going to be a certain amount of convergence. I think also the evolution evolved. Like what if you think through the logic of this, there have been universes that develop life and intelligence for a considerable length of time in our evolutionary history. We're not a recent breakthrough. We're pretty fine-tuned at this point, right? And that means carbon is fine-tuned, oxygen is fine, phosphorus is fine-tuned. And so I think you're going to get something like ATP everywhere. ATP is like a fine-tuned, higher level part of this universe, right? You're going to get something like ATP fucking everywhere.
So this brings me to my last big question is, do you want to present this at an astrobiology conference? Because this is where you could really start, not just the cosmologists and the fine-tuning physicists, but if you're able to present this at the implications of this for universality,
huge. They're huge.
Of life. Yeah.
I mean, I have a sub argument about this that it looks to me like and we argue about this, John. It looks to me like the place where life is optimized for in our specific universe seems to be, to me, to be the liquid water oceans of icy moons rather than the surface oceans of rocky planets. Now, we don't have a lot of examples, but looking around our solar system, we've got 4 rocky planets, and only one of them has been able to hold on to surface water long enough for life, right? You know, Mars, Venus, Mercury, they're all in different ways completely fucked up for life. Whereas we've got liquid water oceans on lots of the icy moons. We probably have a liquid water ocean on Pluto. We've got liquid water oceans all over the goddamn place. And if you think about the delivery of energy, the energy efficiency required to keep liquid water on icy moons, it's so much more efficient than the way you keep liquid water on the surface of a rocky planet. We need a star 8 light minutes away to bombard an entire sphere around itself in order to keep the liquid water on our surface. That's unbelievably inefficient. But if you look at the icy moons, they're just using the tidal energy as they go around Saturn or they go around Jupiter in a slightly eccentric orbit to heat the core and keep the liquid water liquid. That's like, you know, it's like, you know, they're basically like a kettle where all the heat goes into the water. You know, the star keeping the Pacific liquid is like, you know, using a nuclear bomb several miles away to make your cup of tea. It's like, so it seems to me that the more efficient system will have evolved later, and so we may actually be in a transition in our universe from one where life happened under difficult circumstances on the surfaces of rocky planets to one where it's much more likely to happen under the surface of icy moons. You're protected.
Jeez, I'm getting it now. That's a super wasteful acceptation, basically.
A super wasteful acceptation. We were the breakthrough. The surfaces of rocky planets were the breakthrough where this super wasteful breakthrough into life happened. But evolution has since found a much more efficient way of doing that.
Interesting. Yeah.
And another interesting point on that is we very recently discovered in Orion's belt, in the star-forming region in Orion's belt, that there are free-floating Jupiter-sized planets in large numbers forming without stars. And if they have icy moons, we could have enormous amounts of life in liquid water oceans on icy moons going around Jupiter-sized planets without stars. You don't even need the stars. Imagine how many more black holes per unit mass you're getting when you don't even need the star. Anyway, go on.
So it sounds like this is a strong prediction of your theory that we should find life on these icy moons.
I think we're going to find life on the icy moons. I think the conditions for life will be very, very common on the icy moons. And you saw recently, 10 years ago, A.V. Loeb and some of some top guys predicted that there would be orders of magnitude less phosphorus in the liquid water ocean on Enceladus than there are on Earth. Orders of magnitude less. They did a really good study. Blah blah blah. We've now tested the liquid water from the ocean of Enceladus because we were able to sample the plumes that came out from the cryovolcanoes. It's got 2 orders of magnitude more phosphorus than you have in the waters on Earth, right? So, well,
hopefully we won't have to wait too much longer to find out.
I hope not. Yeah, they've got the Europa Clipper heading out there now. We're just a few years away. Yeah. But do you see that? Do you see the pattern here? It's really interesting. It's really interesting. The conditions for life are far better on those icy moons than we have consistently predicted. Very interesting.
So, from my perspective, the way development works is through kind of autocatalytic cycles.
Right.
Positive feedback loops where you have something that, and so I'm trying to, and I can kind of sense, there's a lot of food for thought here. I'm going to read your blowtorch theory next, but I'm trying to figure out what the autocatalytic cycles are, and I can kind of sense them, but I haven't quite put it all together. And
But this is the reason autocatalytic cycles happen and happen relatively easily is because you've got the coevolution of chemistry and biology in an evolved universe. The fucking chemistry evolved. Any elements higher than the ones required for star formation and fusion have been fine-tuned to make it easy for life to come about.
The fine tuning in your view comes from cosmological natural selection.
In cosmological natural selection. But once you have life running, it's a set of nested evolutions. Here's a way of thinking about it. The way I describe it, you've got technological evolution. We're the replicators. We drive it. It happens incredibly fast because we know where we want it to go. Right? That's directed evolution. That's nested inside cultural evolution. Again, we're the replicators. It's slightly slower because we're not consciously as in control of it as we are with technology, but nonetheless, we are driving cultural evolution. We make choices and decisions, so it's directional and quick, not as quick as tech. But cultural evolution is happening inside biological evolution. What?
And that's a problem, as I just wrote about, the rate differential between technological evolution and cultural evolution is a serious problem right now.
It is a problem. It is a problem. But those are happening inside biological evolution, and biological evolution is your classic Darwinian DNA evolution, right? But that evolution is nested inside chemical evolution, the evolution of phosphorus, the evolution of the chemistry that allows for ATP and makes it as good as it is, and chlorophyll, and makes chlorophyll as efficient as it is, right? That evolution is happening outside the lifetime of this universe. There were previous universes where ATP wasn't as efficient. There were previous universes where chlorophyll wasn't quite as good. And it was harder to get life, and it was harder to get... Do you see what I mean?
This is where I'm not quite getting it. The previous universes... So you've got the early universe that you have expansion, contraction, expansion, contraction. Where are those previous universes with respect to that? I mean, where are the previous universes? Are the previous universes are the other galaxies remnants of those, or what? I'm not.
We're talking actual universes. Okay. Let me explain here. In our universe is born at the Big Bang, right?
Yes.
It has a parent universe. We're the result of a black hole in a parent universe.
Okay,
right?
Gotcha. So the idea is that we are the progeny of a black hole from another universe.
Yes.
And the black holes in our universe are parents of new universes.
Yes.
That's kind of the idea. Okay, gotcha.
And if you can imagine,
and I want to jump in with something I've been discussing with Julian, which is this question of if the multiverse is the environment within which these replicators exist, is the environment modified by the replicators the way it is with niche construction in biology? Because there's a change in the selection dynamics when you start constructing your niche. And so there's a benefit to intelligence that is partitioned across both the tuning of the initial parameters and the complexity and purposes, if you will, of the organism, but also in the structure that it has created in its replicative environment, the things that it has, the way it has modified it under selection,
right,
and possibly in competition with other replicators, right? And I don't know how far you could take that analogy, and that to me is the really, like, what this might tell us about the multiverse in a way that we could test would be the way I keep trying to go back to that. And I know Julian is, at present, well, I don't want to speak for you, but I know that's a tough one for you. You don't go there very often, right? But how does the multiverse shaped by the replicators? And I'm very curious about that.
My problem is that just is at the moment seems to me to be just purely speculative. I can't get a handle on it. Whereas all I'm trying to I'm trying to be very what would you say? I'm trying to be very conservative. I know this sounds like a radical theory, but I'm trying to be very conservative. I don't want to freak people out by going into a large amount of speculative stuff where there's no way to get data.
Yep.
If you can get data on that, I'm totally with you on it. But right now, all I want to do is I want to explain our material reality.
Well, for me, the data would be a clue into the nature of the structure of both the initial parameters and the structures that emerge. You talked very eloquently about how Lenny Susskind went to this silly idea trying to debunk Smolin of like inevitable like maximal black holes. Well, Smolin's theory doesn't predict maximal black holes. His theory must be wrong. And then you said, no, it's obvious in all replicators there's a trade-off between the fecundity and the other things that you do. And in biology, that the disposable soma hypothesis has that, right? You put some resources into the germline and some into the soma. So to me, that's something you can clearly get that out of because we know the structure isn't maximizing black holes, but it might be maximizing fecundity with some kind of a trade-off between structure and initial parameters, right?
Yeah, it might. I don't know. Like, okay, let me go. I'll tell you. There's about 3 or 4 different questions here now that I'd like to address. James, let me go back to your initial thing, and I'll just before John came in, I was just going to say, just to clarify, the basic parameters of matter seem to vary slightly. If the basic parameters of matter vary slightly in each generation, you're just going to get these little variations that will have consequences. And so we are inheriting from our parent universe, but we might be slightly better or slightly worse in some aspects because we're slightly different, right? And our child universe is likewise, right? And that exploration is going to lead to some very successful lines and some less successful lines. And we're probably descended from the more successful lines because there'll be more of them, right? So that's how you can fine tune something like phosphorus to be as good as it is. The bond strength of phosphorus is ideal for DNA. It's ideal for ATP. It's just got this nice kind of post-it note, bond strength that's going to be conserved. A universe that varies things a little bit, and then if they have a piece of phosphorus that just sticks really hard and you can't peel off, that ain't going to be so successful a universe,
So
what I'm trying to get my mind around is that a better explanation than it's just the null hypothesis, which is that just all this worked out to be like it is, and the fact that it turned out that way meant it was used, right? That's kind of the null hypothesis. You didn't have to fine tune anything because it was there, and then it worked, and then we got to where we are.
Yeah. Yeah. Yeah.
I'm going to have to think about it some more, but that is the null hypothesis. Everything is random, and if you have enough randomness, then some things are going to work and they're going to get used once you get autocatalytic cycles set up.
Just step back, just take one step back from that and think about what you just said. Just take one step back and go, everything's random, okay? Everything's random, right? Think about the possibility space for all the kinds of matter that could possibly exist. What are the chances?
Well, that's the question.
Yeah.
That is the question.
But this gives you a mechanism for getting here, step by step, through several evolutionary breakthroughs, through a lot of exaptation. It allows you to get to this unbelievably, unfeasibly unlikely situation that we find ourselves in.
Well, that's the question. How unlikely is it? I mean,
oh, come on. Think about the 26, 27 parameters of matter and just run those sliders up and down and see what happens. Everything fucking falls apart. We're at a local fitness peak for those 27 parameters of matter. We're at a local fitness peak. If you mess with any of them by any real amount, the whole thing falls apart. You don't even get matter. You don't even get atoms, right?
No, it's a compelling argument.
Yeah,
George, you got a question to jump in.
Think about the genes in an organism and how unlikely they are compared to randomness. What happens if you just move the sliders on them, right? Do exactly the same to the 27 parameters of matter. You will see exactly the same consequences play out. And the explanation for that fine tuning of those parameters, I think, has to be evolution, just as it is with DNA. Okay.
Thanks. Yeah. So I have one kind of organizational question because I have to leave in 5 minutes, and this seems like a long break. But I also have a question. Maybe you have a second part of the talk, which probably I'll miss because I have another appointment. But so I'm trying to let's take this to be true, right? So you said that let's say the photosynthesis or other chemical cycles were less efficient in the parent universes. So if the mechanism is the black holes, right, and the conditions to form a black hole are enough to produce another universe, how does the photosynthesis affect the black hole formation to enhance kind of the production of new universes? How is ours better in that?
Okay. Well, okay, so photosynthesis is a way of taking the energy that's generated and turning it into complexity and into life, and ultimately those life, the quicker and more efficiently you can generate life forms, the more efficiently they can generate small black holes and thus help the unit of selection, the universe, to reproduce.
You mean after they go all the way to intelligence?
Yeah, but to get to intelligence, you need ways to get the energy that's produced by the stars, whatever, into organisms, into complex organisms, and so chlorophyll, and really helps you do that. It helps you do that. So it's going to get more efficient over time.
But
you'll lock into a crude version of it at some point, and then it will get better in subsequent universes.
So let's take your argument for that the moons are better for generating life or for evolution than planets like ours.
Yeah,
they wouldn't need chlorophyll. I mean, they will need some other mechanism, right?
Yeah.
So yeah,
I want to jump in with an
you
idea.
can see it's possible over the line of universes, as our universes produces offspring over time. It's possible that further down the line of descent, chlorophyll will get less efficient, and something that's good for icy moons will get more efficient over time. That's quite possible. That's quite possible, if you see what I mean.
Thank you.
I can see Julian's arguments from two perspectives. One is that it's just an exaptation. It's exploring the possibility space until it can do something. I can see that. But then I see this other one, which is, if you remember Karen Smith, one of the old Origin of Life guys, he wrote this paper called Genetic Takeover. And he was basically arguing that in the autocatalytic sets of chemical reproduction in the early Earth, the genetic ones just got more efficient at using all the resources, and they just competitively excluded all the others. So it's replicator against replicator in a space of. So this is where his efficiency argument to me really applies. If you have an efficiency of replication and exploring possibility space with your photosynthesizers, then even in these early universes that all end up killing all the life. At the end, the life doesn't affect it, but still, those little replicators, they did genetic takeover all the way through because there is this Evo-Devo process at every scale, right?
At every scale, life is gonna get more complex and more interesting, even in the absence of reproductive success for universes.
Yes,
but so what's going to happen is that possibility space will get explored, possibly inside very unsuccessful universes, because they're wasting a lot of matter on these guys that don't. So it's essentially like the tiny mammals that ended up dominating the Earth, but were very unsuccessful in the time of the dinosaurs or whatever. I'm not saying there's been this kind of stride towards progress in the evolution of universes. I'm saying that we almost certainly come from a line of universes that were kind of bottlenecked and dead-ended and not very successful for a long time because they were producing forms of matter that were very complex but weren't helping the universe reproduce until there was a breakthrough.
Right.
And at some point, you got life that was complex enough to actually manipulate matter to generate black holes and help the universe to reproduce. And at which point you get an explosive takeoff of that kind of universe.
But as you say, you can actually find signs for that in the supermassive to stellar transition, because that's going to be another one of those cases.
That was another massive breakthrough where an inefficient universe that was wasting a lot of matter and not turning it into supermassive black holes, not reproducing with it, that matter complexified to the point where suddenly it made its own breakthrough into reproductive success. And that line explodes off into being far more reproductively successful than the previous. Do you see what I mean? So there's been a couple of massive breakthroughs. And
thank you, Julian. I have to go.
Me too. Thank you, Julian, so much for this. And I'm super happy that Jim is interested, finds this of value, because he's the biologist here. We're all just posers compared to him.
Jim, I would love to talk to you about this again, because you definitely have questions. This is not an obvious.
Yeah, I have more questions. So
this is not a one and done conversation, but I'd love to talk to you about it.
Okay.
All right. Well, so I guess we're going to
figure out some way to do that, and we can communicate by email via the EDU. I want to read your blog now, and then I will get back.
Great.
Fascinating.
Thank you so much.
Yeah.
And I have enormous amounts to learn from you guys. I'm just exploring this territory, and I feel that there's like just fucking lumps of gold just lying around everywhere. This is just unbelievable.
Hey, there's Steve.
You can bring
Dahlia. Clement, do you have any final words for us? Come on.
No, this is extremely fascinating what you're doing, Julian. Really to pull all the strings, all the consequences of cosmological natural selection. Yeah, you really are getting me. You are rekindling my interest to the theory.
I just think adding supermassive black holes as a separate earlier reproductive breakthrough, and then stellar mass separate, and then tech separate, that just unlocks so many interesting implications. It has so much explanatory value, so much predictive value. It's unbelievably, and poor old Smolin didn't have it, because when he wrote the book, we didn't know there were supermassive black holes in every.
So I just got to leave with the one question, which is like, how do you get, once you get technology, well, how does that contribute to the next universe? Because in my mind, it's an evolutionary dead end technology. And
so Jim, Edward Harrison, the cosmologist, wrote a paper that Clement first told me about, the evolution of universes containing intelligent life, in Quarterly Journal of the Royal Astronomical Society, 1995. And he was the first to argue that our intelligence could actually look at the fine-tuning of the universe and hopefully tune it even a little bit better. So he was the first to make that argument, because he was saying we should be able to make universes from nothing, the way that Krauss has said. So that paper from 95 is the first to argue that.
Yeah, once you get consciousness at this kind of level, it becomes reflexive, and you start to craft your own evolutionary future in a way that's really, really interesting. Very, very interesting. I haven't gone into that, but yeah, it becomes extremely, and then that's where you would come in, John, that is intelligent life now taking over the control of the evolutionary future of universes? Probably might well be. It might well be. In which case, we may be in a universe that was tuned by intelligence, and you can think of our universe as coming to consciousness, like a child is born helpless and unstructured and unable to.
Thank you for ending with the Star Child, with Kubrick's Star Child. That's a great ending to this event.
That's where it kind of goes.
Thank you, everybody. I'm gonna hit end record right here. Okay.
Thanks for inviting me. That was great.
Yeah, that was fantastic.
We'll talk again.